Hi, physics class. In this unit we're going to be discussing motion, and while we're doing that, we're going to discuss average speed and what is the difference between that and average velocity, constant velocity, and changing velocity. When we're doing this, you'll notice that, like in that picture that you see with a 13 ball, that each one of those pictures are taken with a strobe photograph. This is a pretty neat website. It's called The Art of Science, where they have got several of these type of strobe photos to help us determine the speed and the motion of different objects. Okay, we're going to be describing motion 3 different ways. The first one is a strobe photo, and the second one that we'll be doing is graphing, and then the third is by using equations to help us describe motion. Before we get into that, let's think about it. What is the motion that you can see in this picture? You'll notice that many of the cars are going very fast. They're tailgating one another, and they are going probably the same exact speed, or else they'd be crashing. If they weren't going the same speed, then that means that they'd be changing speeds, and if they were changing speeds, then they would not be able to be so terribly close as what is happening in the picture. So what we're trying to depict here is that it's got a little bit of constant speed going on. Okay, here are 2 strobe photos where they have a camera lens open while a strobe light is going, and so they can take a picture of many items within so many seconds that they have the aperture of the camera open. And you'll notice that the very top picture that they're showing on here, a 13 ball, where the pictures are very close. This is the same picture that was on the first slide. And when this is happening, you can now make it a comparison to this photo, where we've got just a few more balls in the picture, but it's basically showing you that this is closer together than this one is. So that means that the top photo it has a slower motion than the bottom photo. Since the bottom photo, the billiard balls are farther apart, it means that they are going faster, because they go a longer distance over the same amount of time between the flashes of the strobe light. Okay, here are some more strobe photos where it's drawn by an illustrator. And in the first one, you'll notice that runner number 1, that his distance between each runner is approximately the same distance. So this person is running a constant speed. Okay, and in the next one, let me pull down my screen here. We've got runner 2. You'll notice that the distance between the first runners and the second runners is increasing. The distance keeps increasing, and these photos are supposedly drawn for the same amount of time, so that means that they are going further and further in the same amount of time. So that means that this is accelerating. That means that the velocity and the speed is changing. In this case, it looks like it's constantly accelerating, so that the velocity is changing at a constant rate. Changing at a constant rate. Okay, here's runner 3. What is happening in this photo? Okay, obviously at first he's running pretty fast, and now less distance in the same amount of time, less distance again in the same amount of time, and so forth. So this person is actually slowing down. So if they're slowing down, they are still accelerating, but sometimes it's called deceleration, and it's also called negative acceleration. Negative acceleration. Okay, so that means that this one, the second runner, is actually positive acceleration, because he's increasing his speed and in a positive direction. For conventions in physics, we think of the Cartesian plane, where this side is positive, so like our runner is running in a positive direction in this case. Also, going up is positive, going towards the left side or the west side is negative, and going down is also negative. That's what we call conventions in physics. Okay, now we've got another picture. Okay, this one's showing a stoplight It just turned green. This guy really stepped on it fast. In fact, this guy has to run out of the way. This lady, she's just getting ready to step on it. So now we're not showing a constant speed like we did in that other photograph. Now we're showing in this picture that Paul Hewitt has also drawn that the car is accelerating. In fact, he really is stepping on it. Okay, here's another example of changing speed. Falling objects. Falling objects keep changing their speed. They keep accelerating. For every second, they go 9.8 meters per second faster for every second. So quite often, for the value of acceleration for a falling object, so that's called acceleration due to gravity, okay, we give this value 9.8 meters per second, or meters per second squared. Even if you were going to slow this down and put a ball down a ramp, the ball would still be accelerating 9.8 meters per second squared, even though it's going slower because it's using a ramp. That's a vector problem in itself. Okay, here are some more models of a strobe photo. You'll notice that this one's like that little buggy we have. Anyway, the photo is pretty same distance apart. They're pretty close, so it's not going too fast. It is constant speed. It's not accelerating, so there's zero accel, and velocity is positive, and it is not increasing. Now, in the one below, that's a different situation. You'll notice that the photos, each strobe, that the photo of the car is going a further distance each time. So this time it's going to have a positive acceleration. Okay, a positive value. Okay, here are some falling objects. You'll note that these are two different weights, and that each picture, the weights are falling typically the same exact rate. That's because falling objects are not dependent on their weight or their mass. They are dependent on 9.8 meters per second squared and also their surface area. This is just a neat photo to end with. You'll notice that they put a red dot on the middle of the hammer where its center of gravity is. And just look at the red dot as it goes, and you'll notice that as it gets to the top of its parabola shape, that it is slowing down, and then at the bottom, either the side that they're throwing up or that it's coming down, that the objects are further apart, and we'll talk about more of that in class.